First of all, thank you for inviting me to give this seminar about some recent work. Well, this first one is not too recent. It was done together with Giuseppe Di Benedetto, who is now in Uppsala, Diego Marquez in Buenos Aires, Diederik Roos from Groningen, and some other collaborators in South Korea, Wong Byung-cho, Kim Takeon, and Jung-Hyuk Park. And well, basically I'm going to talk about non-geometric fluxes and stable state resolution in 7 dimensions. So in order to motivate this talk, I want to start by just introducing what is a gauge supergravity in a very quick way. One can wonder about all possible, given a specific supergravity, all the possible deformations that theory allows to have by preserving the field content and the supersymmetry amount and amount of supersymmetry of the theory. And one way of deforming a given supergravity is by gauging a subgroup of the global symmetry of the theory. That can be done in a very systematic way by using what is called the embedding tensor, which I'm going to try to explain in one slide, together with some other deformation parameters which are the supergravity. And we already know that we obtain some gauge supergravities by compactifying a specific supergravity. For example, by using sexual compactification, coset reduction, or doing flat compactification. So let me comment very briefly what is this embedding tensor formalism. As I said before, this is a systematic way to study all the possible gaugings that a supergravity can have. In order to do that, we will promote a subgroup of the global symmetry group of the theory to be local. And this embedding tensor is a quantity, it's a matrix here, that carries two types of indices. The first one, this I, runs from 1 to the number of vector fields that the theory has, whereas the second one, A, runs from 1 to the dimension of the global symmetry group. For this embedding tensor, well, by using this embedding tensor, we will construct, these are the generators of the global symmetry group, and we will construct, by using this embedding tensor, these generators will be the gauge generators, the generators that will be gauged. So basically, this matrix is telling us what is the choice of the generators that we have here that will be gauged. In order for this formalism to work properly, it has to be constrained. It has to satisfy some constraints, which are the quadratic constraints. Which these constraints means that it is this object is gauge invariant by the gauge generators that can be constructed through itself. And it also requires, it is also constrained by some linear constraints that supersymmetry imposes. That is to say, when I impose some supersymmetry, some components of this embedding tensor will automatically vanish. The consequences of having a deformed supergravity will be that the field strength will be deformed, the gauge transformation will be deformed, and the Bianchi identities too. And there will also appear a scalar potential that will be useful to study of the theory and the stabilization of the moduli.
Can you explain the formula?
Which one?
G cross V is stable?
Well, here I'm trying to say that this is the tensor product of these two representations. And then you can decompose this product representation into some one, and some of these representations will be killed by the symmetry.
So in string theory, we expect these global continuous symmetry groups to be broken into discrete groups. And so like, how would you think about some process that explicitly violates the global symmetry in string theory? Like for example, dilettante graviton couplings and some higher derivative term which explicitly violates the U1R.
In my opinion, that would be similar to think about the quantization of the fluxes that you would have when you do the flux compactification, and then you would expect some quantization condition constraint on the components of the guy, which are going to be the deformation parameters of the theory.
I see. So then you would just have the discrete.
Exactly, but here I'm not going to talk about quantized fluxes. Everything is continuous.
Okay.
But this would be the relation. Okay, so as a simple example, I will explain a simple example. If we take maximal supergravity in 9 dimensions, this is the global symmetry group. This is the field content of the theory. Here we have 3 vector fields, and then the embedding tensor. Sorry, I ran out of time. Well, so this embedding tensor, this index runs from 1 to 3 to account for these 3 vectors, and this 8 runs from 1 to 5 to account for the 5 generators. And then I can construct some covariant derivatives in this way, where here I have the encoded embedding tensor. And then the difference, for example, for the field strength, as I said, the field strength becomes deformed in this way. Here I have ordinary derivatives, and here I have the covariant derivatives. Together, some extra couplings here, which are the together couplings, that allow me to couple the next order form, in this case the 2 form, to the field strength of the 1 form. And the same applies for the vector, for the gauge transformation. Here are the ungauge transformation, and here I have the gauge transformation. And here again I have the 1 form gauge parameter that can be coupled to the gauge transformation of the vector field. And this is the difference in the Bianchi identities. Here we see the main difference between having gauge supergravities with covariant derivatives and the Stuckelberg couplings in the right-hand side. So when we solve the supersymmetric constraint, the linear constraints that supersymmetry imposes, in this case we see that we have that the Stuckelberg coupling can be written in terms of the embedding tensor. This is not general. This happens in this case, but it can happen. It doesn't have to happen in general cases. Okay, well, once we solve the linear constraint, we are left with this quadratic constraint. These are the components of the embedding tensor that are left, and these are the quadratic constraints that are satisfied.
So, sorry, when do the Stuckelberg couplings do not depend on the embedding tensor?
No, here when I solve the linear constraint, I obtain that the Stuckelberg coupling can be written in terms of the embedding tensor component. But that is not a general statement. Maybe you have some Stuckelberg coupling, massive deformation, that are not gaugings. Okay. And in this case, that doesn't happen.
Okay,
but it is possible.
The deformations are
yes. Well, once I solve the quadratic constraint, I obtain this set of solutions. Well, actually, I have more than this solution.
Where did Susie come in this story? I think
Sorry?
Where did supersymmetry come in?
Well, here you impose the closure of the algebra on the transformation of the scalar field, and there are some constraints. And you impose that on the vector field, and you obtain some constraints. And you start to identify embedding tensor components with the Stuckelberg.
Also the linear constraint.
Exactly, the linear constraint. Exactly.
So what are the indices ij?
I and j are SL2. SL2 indices, because the theory is SL2 r plus square times SL2 is the global symmetry group.
Very nice. So we're
In 9 dimensions.
SL2 doublet or triplet index?
This is a doublet.
Doublet, oh, of course, yes, yes. Okay.
Wait, when did we get a 9 dimension?
Here's an example.
This is an example.
Oh, okay, thank you.
I said here that this is an example.
Okay.
What did you say about linear constraint?
Yeah, that comes from Susie. I mean, the one that you were asking about before, which representations are done.
Okay, but basically what I'm trying to say is when we solve the quadratic constraint, we obtain these possible solutions for the different configurations of theta and kappa, and when we calculate we plug these configurations in the gauge generator, we can identify what is the gauge group that has been gauged. Okay? This can be done for any supergravity, and that is what we one more thing is that we haven't talked here about compactification of anything, and we can check that all of these gauges can be obtained by compactification of 11 or 10 dimensional supergravity. Okay, down to 9. This is a work by Bersuf and the other groups as well.
What is ID?
ID is an identifier of the 1, 2, 3. Okay, we can play the same game for another supergravity, for half-maximal 8-dimensional supergravity. In this case, this is the global symmetry group, without taking into account the trombone. These are the embedding tensor components, and these are the quadratic constraints of the theory. And when we play the same game, we see that we obtain these three types of, these three orbits of K. And what we see is that the first one can be obtained by compactification. There is I don't remember the reference, but there is a reference that allows to have this gauging. But the other two ones cannot be justified by any compactification of 11 or 10-dimensional supergravity. And then this is the general picture that I would like to explain. So we start from here. We know that we obtain compactification lower limit and gauge supergravities from toric compactification. We obtain a subset of gauge supergravities by self-Schwarz, process reduction, plus compactification. But this embedding tensor is allowing us to have access to a set of non-geometric of gauge supergravities that in principle don't have a higher dimensional origin. But we don't know how to justify it. And we are calling for some duality construction, as for example double field theory, to try to know whether these duality construction are able to justify this deformation from compactification. Well, so this is the goal of the talk. In the first part, I will talk about the basis of double field theory. In the second part, I will make contact from double field theory to the gauge supergravities that